Hi statistic user, and welcome to this ultimate tutorial video, namely the one of simple logistic regression. In this tutorial video we're going to show you how to use this method in order to search for associated factor related to a phenomenon. So contextually, you need to know that logistic regression is applied in case in which we have a qualitative variable with two modalities. That means the variable is binary. The binary variable that we need to explain using k, qualitative or quantitative variables. So the explanatory variable is qualitative with two modality or being binary. That means that's the foundation of logistic regression. And to explain your binary variable, you need to have explanatory variable in the number of k that can be qualitative or quantitative in order to explain your variable. So logistic regression is mostly used in epidemiology in order, for example, to identify the disease related factors, or to search for the death causes or patient survival. So you need to know what cause a particular disease. You have factor that can be related to the disease. You can make a binary or a simple logistic regression in order to see what influence the occurrence of your disease using factor that are explanatory variable that need to be whatever qualitative or quantitative. So what's the specification of the model? So as I told you very earlier in this tutorial video, y is a binary variable that have two modalities: 0 in case of non-occurrence of the situation, and 1 in the case of occurrence of the situation. Y is supposed to be random, and your explanatory are supposed not to be random variables. Then the aim of the simple linear simple logistic regression is to explain the occurrence of a phenomenon. So the phenomenon that is binary, that have only two modalities: success and other eventuality. So we are looking for the probability of success. If our first modality is success, for example, we are searching to estimate the probability of success. And you need to know also that in simple linear regression, or generally in logistic regression, we work in terms of expectancies. So the main objective is to predict or to explain a categorical variable y from recollection of descriptor variable that can be enumerated as x1, x2 till xk. It's sort of like highlighting the existence of underlying function link. So we are searching for a underlying function link between our our explanatory variable, that is binary variable, in function of descriptors. So you need to know that in this kind of specification, our function that related y to the factor to the descriptor cannot be a linear function because y take only two variables. So you cannot use linear function. Linear function is not required, is not appropriate. It's not appropriate in this kind of situation if you need to explain your main variable that is supposed to be binary in function of many other variables, even though there was only quantitative. So we need to search for a functional relationship that cannot be linear in this kind of situation. So when you look at the expectancy of y, taking only two variables, once use a logistic function. The logistic function is a function that's defined by the ratio of exponential of a number over 1 plus the exponential of number. That's take the form of a probability because this function take its value between 0 and 1, and it's a positive. The expectancy is equal 0 to 1. So we can use logistic function defined as so in order to model the probability of that is binary, to model the probability of occurrence of our phenomenon that is that only have two possible realization. Y distribution, we can say that y follow the Bernoulli's law of parameter p. P is the parameter that we are going to express to estimate using a logistic function. So if we have two modality, we can suppose that our variable follow a Bernoulli law of parameter p. And if we apply the logistic transformation to our probability, we can see that our logistic can be written as a logarithm of our parameter. A parameter that we previously expressed in function of in terms of logistic. We can also find x in this relationship in order to you will find a relationship that give the logic in function of your parameter. So the challenge in the logistic regression is to estimate a coefficient. As you see, when we make a transformation of our parameter, you see that our parameter is a relationship that is not now only 0-1 realization, but the logarithm of our parameter is a relationship that can be take its value in R. So we can use linear regression right now in order to make to model a logic of our parameter, because our parameter take its value in R, in numeric number set. So the challenge is to estimate beta 0, beta 1 till beta k, so that the logic of our parameter that is expressed like that can be written correctly. So what can we estimate logistic coefficient. In multiple linear regression, the method of the ordinary least square is known as minimizing the sum of square of error, error square, and this method is not appropriate. It's not interesting in the case of logistic regression. So we will use in logistic regression a classical method of maximum likelihood. That is a method that allows to estimate a parameter of a law or a model. So we use maximum likelihood method in order to estimate parameter, and we will come back in this method in a second. So we'll just take an example of binary variable that have only two modalities, 0 and 1, and we have only one explanatory quantitative variable x. So we have our population, we have an n sample of our variable. So we have a n couple of variable xi and xi yi xi. So we are going to use this sample in order to estimate our parameter. We have for each observation I, the variable yi is equal to 1 with the probability p of x equal to the probability that y take a value 1, knowing that x take a value xi, and 0 with odd probability. So defined as so, y follow the Bernoulli law with parameter 1 and the probability, so that the probability is given by the logistic function that define a probability that can be used in order to define the probability. So in likelihood, in maximum likelihood method, the first thing is to estimate the likelihood of our joint function. The likelihood is a probability that to observe our sample, So that which means that for every of our n independent variable, the probability, the likelihood is equal to the probability that x1 take a realization of our variable for the first observation, x2 take a realization of our variable to the second observation, and so on. So using the independence of our function, we can write our likelihood as a product of every probability. So since the observation are considered to be independent, we can write our likelihood as a product of every single probability. So if we use a Bernoulli law, we can write our probability for every xi as you see on your screen, so that the likelihood can be written as a product of every single probability. But if we use a logistic model that is given as follow, as we show you very earlier in this tutorial video, we can write a likelihood as a function of alpha 0 and beta 0. So the objective of the maximum likelihood is to maximize the probability to observe our sample, to maximize our likelihood function that is written as so. So for the reason of simplicity, we will just run the maximum of the logarithm of our likelihood function, that is the same as the maximum of the likelihood, given that when we calculate the logarithm of our likelihood, we have a function that is very easy to manipulate. So to find the maximum of our the log of our likelihood function, we use numeric method called Newton-Raphson in order to search for beta 0 and beta 1 that maximize our likelihood. That's the point that annul the partial derivative of our log likelihood function. So the interest is that once beta 0 and beta 1 estimated, we can calculate for all I the probability of success given the different observation. So with the logistic model, we can write the logic of this probability as a combination of our estimated parameter. So once we have compute our coefficient in our logistic model, one of the main challenge is hypothesis tests on our coefficients. First of all, the global test of significance of our model, and to test this we will use our likelihood ratio test. Likelihood ratio test in which we have null hypothesis, no connection between y and the xi. That means that we suppose that every coefficient is in our linear model, is in our logistic model null. That's the null hypothesis, and its alternative is that the model makes sense. That means that at least one coefficient is different to 0. So to test this hypothesis, we can consider a simple example, the case with a single explanatory variable. We can come back to the single explanatory variable. So the principle of the likelihood ratio test is to compare the likelihood x with explanatory variables on the H1 hypothesis with the likelihood L0 without explanatory variable. So is under the null hypothesis. Intuitively, we can think that if likelihood on the H1 is superior to the likelihood on the null hypothesis, then the variable bring to estimate the estimate of the probability of y. So in likelihood test, we consider a statistic d that is given on our screen that is shown to follow the chi-square at 1 degree of liberty. So the interpretation is that the non-rejection of H0 in case of non-rejection of H0, the model does not make sense. Does not make sense at anything to do estimate of probability of y. So model doesn't make sense. That mean that we are wrong, supposing that the logic of our probability is a linear combination of our explanatory variable. So in the other hand, the rejection of our null hypothesis means that the model makes sense, given that x give the estimate of our probability. So there exists a link between our probability and our explanatory variable. So also to interpret our coefficient, we can remind you a notion about odds ratio that you can find on my previous tutorial. The odds ratio that is defined as a measure of association between exposure and between exposure to the disease and the disease himself. So the odds ratio is calculated, and the ratio of those probability, the ratio of odds to be exposed. The odds to be exposed is the ratio between the probability of exposure and of exposure that are sick and the exposed person that are not sick. And the odds ratio of unexposed is a ratio between the probability of non-exposed that are sick and non-exposed that are not sick. So after odds ratio calculated, we can be using it in order to interpret our coefficient. So you need to know also that when the odds ratio is when our probability, the probability of to be sick is low, inferior to 10%, the odds ratio is sensitively equal to the relative risk. So the odds ratio can be calculated and interpreted as follows. When the odds ratio is equal to 1, you can suppose that there is not association between our disease and the exposure. There is not association. And when the odds ratio is more than 1, we suppose that exposure is a risk factor to the disease. And rather, when odds ratio is less than 1, the exposure is a protective factor to the disease. So we can use, we can conclude that odds ratio is equal to 1 when chi-square association test is not significant. So to interpret a coefficient, we will take we can also see that in single explanatory variable, the logic of our explanatory variable can be written as a combination of x variables. So the difference between the logic of the probability of to have the first modality of our explanatory variable and the logic of the probability to have the second modality of our variable is equal to beta, so that the logic of the ratio of probability of success and the odd event is equal to beta 1, and we obtain our odds ratio as an exponential of beta 1, so that the exponential of the coefficient can be interpreted as an odd ratio. We will return that odd ratio as we show you the calculation very earlier a minute ago is can be interpreted as a exponential of beta 1. So we can notice that same in the multiple case, but the odd ratio are adjusted on the other variable xg. So we suppose that we x is quantitative variable, odds ratio equal to exponential of beta 0, we can have this interpretation in this particular example where our odds ratio is equal to 2 when we have as variable age in tens of years. If we have as explanatory variable age in tens of years, we can show the following interpretation when odds ratio is equal to 2. So going from 20 to 30, multiply the risk of disease by 2, or age 16 to 17, double the risk of illness. And this is underlie the strong hypothesis that the log linearity, under the hypothesis of log linearity of each wish of x, which is to be verified. So that's the end of this tutorial video. I hope it helped you understand the simple linear regression. I hope to see you very soon in the other in the future venture.